Okay, so it says that
yeah,
event has been live streamed. Got it.
Okay, great. Fantastic. Yeah, so
Cool.
first of all, thanks, Konrad. It's really great to have you here. I'm
Shall
gonna
we
let
start,
Lorenzo.
sorry, shall we start the recording as well?
Oh, yeah. Just as a backup in case the live stream fails.
Maybe should I share my screen, or is it because? No?
Yeah. Fantastic.
Okay, and just hold on a second, because it's interesting. Because sorry. Okay, because I had the live stream page on YouTube open as well, because it opens it automatically. Yeah. And I was hearing everything 10 seconds late. People talking, saying, where are you guys? I mean, I don't. So it was
it's a bug in
surreal.
In the matrix.
It's a very surreal. So now I'm going to start the recording. And Konrad, would you be happy to have your talk recorded as well as live streamed on YouTube?
Yes. That's really great. Thanks a lot.
That's really great. Thank you. That's Emiliano. On to you.
Yeah, no, I will ask Lorenzo to kindly introduce Konrad. I just wanted to welcome everybody to the first edition, the first seminar, the first event of this rebooted seminar series. So I was saying before, this is just a continuation of what we've been doing for the past few months with Giovanni and Vasilis from the Turing. So we had this interest group at the Turing on privacy and machine learning, and we've decided to broaden the scope a little bit, also following some kind of survey, very informal survey that we ran a couple of months ago. So we will consider all aspects of security and privacy in machine learning, for machine learning, from machine learning, and so on. So I'm very happy to welcome Lorenzo in the management team, let's say, as a co-organizer of the seminars. So we're all based in London, and so we call this the London Privacy and Security Machine Learning, but obviously everything is going to be virtual. So we'll have speakers from all over the world. We try to have Wednesdays, every 2 Wednesdays, 1 p.m. UK time, but we will move the time also to adjust for like time zone differences. Whenever we have, next seminars, we have someone in Singapore, then we'll have somebody in the West Coast. So we'll have to shift things around, and that's really great. So we have a mailing list and a website, presec-ml.github.io, and there's the link to join the mailing list. There is a Google Calendar you can subscribe to. We have a Twitter account, so we're all social. And we're very happy if also people want to volunteer to give talks, or they want to organize other sort of events. Please get in touch with us. So there is one technical thing I wanted to say. So we'll advertise the seminars on Twitter and on the mailing list, and we post the YouTube link for the live stream, but also the Zoom registration link. I'm sure you've seen. If you're on the mailing list, we'll actually post also the meeting details on Zoom, so you can actually join the seminar on Zoom without having to register. If you don't want to, just don't. It's not going to be the standard link, that you click and you just join. You have to, go on Zoom and click on join meeting and sort of manually add the meeting ID or the passcode, and you will join. Just a technical thing. We just keep the meetings registration only to avoid Zoom bombing. So that generates unique code and so on. Anyway, so this is all for me. If you have any questions, please use the chat. Also on YouTube, please use the chat. We'll monitor it. Of course, the YouTube chat, the YouTube stream is a few seconds delay, maybe 30 seconds or so. So if you ask a question, it's not kind of sync in real time, but whenever we can, we'll make sure to prompt questions to Konrad. Unless Konrad, you prefer all questions to be at the end. Up to you.
Doesn't matter.
So that's okay.
Yeah.
So we keep everything in the end. Yeah. Okay. So we'll stop the live stream after the end of the talk, plus, answering questions that were posted on the YouTube chat. And so, then we have Zoom-only participants that, can have a bit more informal Q&A. Let's say it's not recorded, not live streamed. So you can be as politically incorrect, although, respectful, of course, as you want. All right, that's all for me. Thanks. Thanks.
All right. Thanks, Emiliano, for the kind introduction to our rebooted seminars. And it's a great pleasure for me to have Konrad here. I mean, Konrad and I have known each other for some time now, but it's a true pleasure. And of course, I can introduce you, Konrad, by reading a little bit of his bio on his webpage, which I'm going to be doing now. He's a professor of computer science at TU Braunschweig, where he heads the Institute of System Security. He also worked at the University of Göttingen, TU Berlin, and Fraunhofer Institute first. His research revolves around computer security and machine learning. And his group has been working on really novel and very interesting piece of research at the intersection of the two subjects for detecting computer attacks, for analyzing malicious software, discovering security vulnerabilities, and so forth and so on. But I guess, what I would like to really mention about Konrad is that he's one of the shouldn't say oldest, but, the most renowned and respected, at least for me, scientist that has been working at the cusp of machine learning and security ever since I've been following his research many moons ago. And he's one of the persons that I truly look up to when talking about computer security and machine learning together. So I'm sure that the talk today will be thoroughly interesting. And I would suggest you to also follow Konrad's research because it's truly outstanding. And by the way, he's also a very distant academic relative of Carl Friedrich Gauss, although he claims that this doesn't help when solving maths problems, unfortunately. So Konrad, the stage is all yours. And I'm going to be removing my camera as well so that you can have full visibility. Thank you.
Okay, yeah, so thanks a lot for this very warm introduction. So I'm also very happy to be here, and I'm also very happy to present my research in this kind of reboot of the seminar. And I jump in, with the following slide. Let me move here to my slides. I want to talk about machine learning, but a little bit from a different perspective. So I guess you all know that in the last, let's say, 5 years, there has been a lot of work on attacking machine learning systems. And what you can see here is a typical pipeline that you would see in such a research. And we have on one side, on the top, the training phase, and on the bottom, we have the application or inference phase. And now these little needles and these little dots that you can see, they correspond to all of these different threats and attacks that have been introduced and discussed in the last years. And there's all this magic about adversarial examples on the application phase. And there's this not so much magic, but still magic on poisoning and backdoors on the training phase. And then there's also these things that relate to privacy and confidentiality, like membership inference, and so on and so forth. A lot of super cool stuff. Now, unfortunately, I cannot talk about this cool stuff, but I have to talk a little bit about boring things. And I made this fascinating animation here to introduce some boring boxes. The reason is that in practice, machine learning systems always employ a preprocessing phase. So these systems do not directly operate on raw data, but instead some preprocessing is in the way between the original data and the learning algorithms. And I guess we all agree that preprocessing is super boring, and this is the reason that it's not part of these papers that we have all read and that we all like. So things like normalization, parsing, scaling, feature extraction, feature reduction, things like that, all of them are typically not discussed. And I like to start with looking at this aspect today and talk a little bit of the work that we've been doing in the last year on attacking scaling algorithms. And scaling algorithms, as you know, are an essential part in computer vision. Actually, any neural network, I would say most of the neural networks used in computer vision require scaling to be done before they can work on some images, because these neural networks have a fixed input size. So you have to scale your input images to the size, and then you can work with all of this great image recognition things. And these attacks that I want to talk about, these image scaling attacks, they have been the topic of a paper that we published in the last year. And I have to say, of course, I didn't do this alone, but instead a team of people worked on this. And most importantly, my PhD student, Erwin, worked on this. And I'm very happy that this is the last time I will call him a PhD student, or hopefully the last time, because he will defend his thesis in 2 days and then turn to the other side and become also one of those so-called P people, those either postdoc or professor, if you know this kind of P people. So this is where he moves to, and I think he did a lot of the work behind these things that I will show you in the following. So let's start with the origin of image scaling attacks. So in 2019, I saw an interesting paper at Usenix Security. And this paper introduced these attacks. And the authors very nicely derived the attack from adversarial examples. So essentially, this is a new variant of an adversarial example, at least at the first glance. And I have written here the optimization problem that they present in this paper. And maybe shortly, I explain what's going on. So what we want to do is the following. We have an image S. You can see this here. Can you see my pointer?
Yes, yes, we can see it.
Yes. So you can see, we have an image S, and we want to add a little bit of slight noise onto this image. And this noise is typically called a perturbation, and it's added to the image. And then when we scale the whole thing and subtract some t, we want this to be very small. And t is our target. So what we want to achieve is that when we scale the image changes and becomes our target t. And typically in these optimization problems, the goal is to make these modifications as small as possible. So we minimize on the perturbation. And that's from the design very similar and very close to how adversarial examples are constructed. And as a result, when I had the first look at it, I thought like, this is just yet another variant of this work. There are like thousands of papers on adversarial examples. So is this really cool? And then we implemented this and built some examples just to see how these images would look like. And here's an example that Erwin prepared. So on the left, you can see this cat, and on the image is a little bit of noise. And if we scale this image to a specific size, we get the dog on the right. And I found this quite impressive because what's happening here is that the image really disappears, the original image, and we can only see the scaled version. In contrast, however, to adversarial examples, if we look very closely into the image, we can see a small pattern, a small grid. So I'm not sure if you can see it on your screen, but at least I can see it on my slide. So there's these kind of very fine dots in the image of the cat. And these fine dots are responsible for the attack and create this dog image on the right. I can also do this with other images, so I'm not restricted to cats and dogs. Of course, this is kind of the best thing you can do, but you can also do this here for two cities. And again, if you look closer, you can see a fine pattern. Still, I would argue that if you see an image and there's a little bit of grid or a little bit of pattern on the image, you would not suspect that it completely changes its appearance once it is scaled. So I was very impressed by these results, and we decided to look a little bit closer to what is going on with this attack and how it works. And the first thing that we noted, and also the original paper, by the way, is that this attack is inspired from adversarial examples, but it has a completely different threat model. So here we attack the scaling algorithm. So what is happening afterwards doesn't matter. So the attack is agnostic to the learning methods and agnostic to the features that are extracted from the image. And this makes it a very powerful attack because we do not need to know anything about what's going on there, complex neural network, convolution, max pooling, whatever, doesn't matter. If we can successfully fool the scaling algorithm, everything following will automatically be under our control. What we need to know, however, is the scaling algorithm and the output size. Both of them are typically not so difficult to guess. So what can we do with this attack? So I prepared 2 examples to illustrate that this is not only a kind of academic attack, but could be used to cause real damage. So on the left, you can see a poisoning attack. So what I prepared here is a traffic sign. The traffic sign shows a 40 in the big version. And if it gets scaled down, we can see a 10. So this means a neural network trained on this image would see the 10, and then would learn that a 10 is associated with a traffic sign 40. And maybe a car would then drive a little bit faster. It maybe cause problems. That's an attack on the training phase of machine learning, but we can also attack the application phase. So on the right, you can see a passport photo of myself. It's a typical biometric photo. So you have to watch straight into the camera, and you have this kind of very unfunny face. But nonetheless, this is used on our passports in Germany. And of course, there's also a digital version of this image. And I would be able to add an image scaling attack to my passport photo. I could at least transfer the scaling. I could exploit the scaling attack and then generate a new image once this is compared in a face recognition system. And as an example here, I chose somebody who looks different than me, and he also has a gun in his hand. So this would be an image that you would typically not expect on a passport, but the neural network would see this image if it is scaled to the correct size. Okay, so this maybe shows you that the attack can have an impact. So maybe, now you will say like, but isn't this really a problem? I'm using scaling algorithm X, or I'm using machine learning framework Y, so I don't care. Well, we looked at 3 major machine learning frameworks, and in the respective versions that we looked at, unfortunately, most of the scaling algorithms were vulnerable to this particular attack. So you can see the table here, and whenever there's a red thing, this indicates that the implementation is vulnerable. And even worse, often also the default scaling algorithm is affected. There are some green crosses which indicate that not every scaling algorithm is vulnerable. And interestingly, not every implementation of the same algorithm behaves in the same way. So for example, B-cubic scaling, bicubic scaling used by all of them sometimes is vulnerable, sometimes is not. So this seems like an interesting case, but at least there is a problem, and it is present in these respective versions of the frameworks. So this led us to the question of why is this happening, and where is actually the problem? Because I thought at least scaling is well understood, and that's why it is so boring, right? And this is why maybe neural networks are so fascinating, because they have these millions of parameters and these thousands of layers, and then there's this very simple algorithm. So what's the problem? And unfortunately, reading the original paper from 2019 did not help at all, because the authors were kind of maneuvering into the direction of robust machine learning. But this has nothing to do with robust machine learning, and it even has nothing to do with machine learning, despite being the topic of the seminar. But actually, this is all about scaling algorithms. And if we can fool a scaling algorithm, anything that happens afterwards is under attack. So we need to think about what goes wrong inside these scaling algorithms. And what we did is we started to look at the implementations of these 3 machine learning frameworks. And we tried to find out what's happening inside these algorithms. How does the scaling work? And we found out several things that we did not know. Maybe somebody from the area of computer vision would say like, oh, all of this is completely clear to me. But we as computer security researchers, we were kind of really surprised to see these kind of steps develop under our analysis. So first, what we learned is that scaling algorithms do not work on the 2-dimensional image directly, but instead they first work horizontally and then vertically, or the other way around. And this means from an analysis perspective, from a signal processing perspective, we are actually dealing with a 1-dimensional signal. So we just have this maybe column or row, and this is shrinked together as part of the scaling. So this was an interesting insight. And then we noted that the scaling itself in all of these algorithms is very simple. Essentially, there's a group of pre-computed weights, and these weights are applied to the pixels of the rows and the columns, and then they're kind of aggregated together with the help of these weights. And these weights define whether this is a B-cubic or B-linear or nearest scaling. Okay, interesting. So we went further and started to think about what this actually is, what we have here in our hands. And it turns out that this is very similar, if not identical, to what people in signal processing would call downscaling. So you have a high frequency signal, this is your long column, and then you reduce it to a low frequency signal, this is your scaled column or row. And the scaling does not just pick some pixels, but it performs some computation on this signal, and this looks like a convolution. So what we actually see in these scaling algorithms and their implementation is the signal of the image is downsampled with a convolution. And the pre-computed weights, they take the role of the so-called convolution kernel, which is the function that defines how this is aggregated. So let's have a look. I prepared some examples. So here you can see 3 of these kernel functions. These are not machine learning kernel functions, but statistical kernel functions. And you can see if the kernel function, let's pick the blue one, if this is just a linear function, we have a bilinear scaling. If this is a nice curvy cubic function, we have a bicubic scaling. And if this is a very peaky and edgy function, then this is, for example, the nearest scaling. And for all of the other scaling algorithms, we can construct similar kernel functions. Now, maybe you didn't came to this seminar to learn about kernels inside convolutions, inside scaling algorithms. Okay. But the interesting thing here is now that we have a very nice and also very simple model of what is going on in a scaling algorithm. And it is independent of how the algorithm is named or how these weights are defined. And it enables us to reason very generally about the process of scaling and then about the attacks. And this is what we did. And what we noted, and what then also was confirmed by all of those people we talked with that are very well versed in signal processing, what's happening here is we scale a signal down, so we do downsampling, but there's no low-pass filter. So what does it mean, a low-pass filter? So I will go into a little bit more detail soon, but for the moment, if you scale an image and you use a inappropriate scaling algorithm, you sometimes can see these alien effects. So there are some structures and patterns typically appearing at the border of objects or at the edges, and these are called aliasing effects. It's something that we do not want to have. And therefore, in signal processing, typically a low-pass filter is applied. And this low-pass filter avoids high frequencies leaking into the sampled signal. Now, in our setting, however, we do not see a typical aliasing effect, but we see something that I would call a malicious aliasing effect. So the attacker exploits this very property to create these completely changing images. And we can make it much more simpler if we take on maybe the computer scientists or even the computer security glasses and look at what's happened to the pixels in the image. And the truth is, during scaling, most of the pixels of the original image are ignored, or they have a very, very low weight. And as a result, only very few pixels receive a high weight during the scaling. And thus, all of what we see in the scaling depends on these very few pixels. And that's kind of a very bad idea. So here's an example that shows how these factors influence this downsampling. So we can see here a bilinear kernel, and it's applied to generate a 2-pixel signal that is on the right side. And on the left side, we have more pixels. And only those, the pixels are here, these kind of lines with a dot on top. Only those these 3 black points are pixels that are actually considered and contribute to the scaled version of the image. All of the other pixels, so all of these lines with a white dot on top and no black dot, they simply do not contribute. So whether they are present or not doesn't matter. And during an analysis that I will not sketch here completely, we could kind of narrow in on those factors that really contribute to this phenomena. And this is on the one hand, the scaling ratio. So how big is the difference between the scaled version and the original one? It depends on the shape of the kernel function. Is it like a peaky kernel function, or is it like a very wide kernel function? And it depends on the width of the kernel function. So is it like very wide, or is it also very peaky? And we did a lot of experiments and could kind of confirm that these factors essentially describe when and how the attacks work. I'm just showing one example. So what you can see here is a slide that shows a part of our evaluation results. So what we did is we took 600 image pairs from ImageNet, and we transferred one into another using an image scaling attack. And as victim, so to say, we use a common neural network in computer vision, VGG19, and we did object recognition on the scaled images. And if the scaled images contained the objects from the target, the attack was considered successful. So what's missing here, and this is what we did, is how does a human perceive something? Something also an issue with adversarial examples, at least in my opinion. Very often the people say, if I can fool the machine learning algorithm, I already succeeded. But the question is, would a human perceive something different on the image? Only then the image is successful. Otherwise, we just change all of the pixels and then it looks different. And where's the kind of contribution? So what we did is we run these experiments, and then we gave the images to humans and asked them, do you see anything suspicious? Does this look like a cat or does it look like a dog? And if they said it looks like a dog, in our first example, this would be an visible attack and unsuccessful. And we did this experiment for the different factors. I'm showing here as an example the scaling ratio. And you can see that in this plot, whenever there's a red bar increasing, more and more of the attacks are invisible. And for a scaling ratio of 10, all of the attacks were invisible. And for a more realistic scaling ratio of, let's say, 4 to 5, the half of the images were successful in the sense that they would fool VGG19, the neural network, but a human would still see the original image. So this was kind of great because with all the other factors and scaling ratio, we had kind of a very good feeling for what was going on. And we essentially could dive to the root cause of the problem. And then something happened that happens rarely in adversarial machine learning. We had the root cause for the problem, so we could start to think about working defenses. So not kind of trying around or obfuscating something or making something more random, more non-deterministic, but instead we could just try to understand how can we eliminate the vulnerability with the help of these root causes, with the help of reducing these factors, the scaling ratio, the kernel shape, and the kernel width. And this is what we did. And we started by asking a simple question. So what makes a good defense? When I was preparing the slide, I already noticed that this is a question that boils down to the question of what is a good democracy? Well, a good democracy is the following. Everybody should contribute to it, so vote, and everybody should have the same weight in this voting process. Yeah, and the same holds for scaling algorithms. So if I scale down an image, I want the scaling algorithm to look at all pixels of the image, not just a few, and all of the pixels should have the same weight. And if I explain this to you now, I would also argue that this is maybe really obvious. Surprisingly, when we started working on this, this wasn't clear at all. But now looking at it, it seems like a very natural thing. And we thought, okay, so let's design a new scaling algorithm, the robust scaling algorithm. This was our first idea. And we simply looked at the factors and said, okay, we cannot change the scaling ratio. The scaling ratio is defined by the application and the image, so there's no choice that we can make. But we can adapt the kernel function, so we can change the width of the kernel and we can change the shape. So what we could do, and this is our proposal, we say the kernel width is adapted to the scaling ratio. So if the scaling ratio is very big, so we have very few points that are considered, we want the width of the kernel to cover all of the region in between. As a result, no matter how large you downscale or upscale, the kernel will always cover all of the pixels. Cool. And we wanted that all of the pixels contribute equally. So this means if we have this window and we look at the function of the kernel, it should be a flat function. And you see on the right this magic flat kernel function. Now we were kind of very happy with this result until we looked a little bit into what we have written earlier in our paper, and we found out this already exists. It has always been there. Area scaling is the answer to our questions. And maybe you do not know area scaling. It's, I would say, an unpopular scaling algorithm because it's a little bit slow and a little bit blurry. But it's a scaling algorithm that exactly performs what I described just as our idea for robust scaling. This was, on the one hand, of course, a little bit disappointing. We were already thinking about naming a new scaling algorithm, and now it turns out this already exists and it's pretty straightforward. And it's also part of all the frameworks. But on the other hand, it was kind of also great because now everybody could use it and it would save us from this attack. So we did some experiments to demonstrate that this is really a working defense. So here you see on the left a cat image. The cat is the target, so we shouldn't see the cat, but instead we should see this kind of small espresso cup. And the attack fails if the cat is not visible anymore and we can see the cup. And left, you see normal nearest scaling, and on the right, you see area scaling. And it's clearly obvious here in this example that the attack does not work anymore. The cat is slightly visible in the back, but the image mainly is defined by the picture of the cup. Now, we did this with, again, our 600 image pairs, and we could verify for each of these pairs that the defense works. And the great news is area scaling is widely available. You can use it right away. The bad news is it still contains artifacts of the attack. So you maybe can see the cat. So I magnified a part of the eye from the cat. And it's slightly blurry. So this is the reason why people typically do not use it. But so these are the disadvantages. And then we thought, okay, if we cannot invent a new scaling algorithm, so maybe we can do something different. Maybe we can fix the attacked image, and then every possible scaling algorithm can be applied securely. So what we designed was a defense that reconstructs, to some extent, the original image, and by doing this, removes the attack. So if you come from the world of adversarial machine learning, you will say like, hey, wait. Removing such a fine perturbation from an image is very difficult, if not impossible. So this means that it's extremely hard to find out what the attacker has been doing and how he very carefully added these very fine noise onto the pixels of the image. But this is different in our case. We are not, again, working with a neural network. We're working with a very simple scaling algorithm. So we know exactly what pixels are affected by the attack and what weight they have in our scaling algorithm. So if we take one particular scaling algorithm, let's say nearest scaling, we can very precisely determine which pixels contribute to the attacks and which do not. And our idea is now very simple. We just take those pixels that contribute to the attack and reconstruct them with other content. Sounds super simple. But when we thought about this, it turns out that this is a research question in its own. And there's a whole field in computer vision that is concerned with reconstructing regions in an image, like reconstructing some noise or reconstructing some missing information. But in our setting, we can do something simple, and we did this. So we can say, let's put a window around those affected pixels, and then just select one of the pixels in this window as a replacement. This is what you can see here on the image. So you can see in red the vulnerable pixels. Those are the pixels that need to be reconstructed. And in blue, they are the benign pixels. And as we know, as defenders, the algorithm, we are 100% sure that this is the case. There's no way around, because we know exactly what our scaling algorithm will do. So what we do is we take one of the blue pixels and replace the red ones with it. And we propose two strategies to do this. The simple strategy is a random filter. It just replaces the vulnerable pixel with some random pixel. Okay. A little bit more advanced is the median filter. The median filter goes over the color channels of this window and then replaces the median of the color for each channel. So we do not take a concrete pixel of the image, but rather we reconstruct the pixel with the median of what's going on in this window. And to be on the safe side, we make our window as large as the kernel width in the previous defense. So we make it so large that all of the pixels are covered and nothing is ignored. So again, we make sure that this computation has a democratic process. So it looks at everybody, and everybody can contribute to it either by being randomly chosen or by being part of the median computation. So this is how this looks like. So again, we can see no defense, a nearest scaling is used, and we can see this cat, very nice. And then we have two images where we reconstruct the original image and then scale down. And in this case, we very nicely see this cup of whatever this is, likely espresso. We did again an evaluation on the 600 pairs that we selected, and we could verify for each of these pairs that the defense works correctly. The advantage of this approach is it is another pre-processing step. So we can just add this defense in our pipeline, and we can then later apply the scaling algorithms that we want to. Of course, there's a relation between the defense and the scaling. So if we pick scaling algorithm X, we need to compute what pixels are affected, and then we can run the defense. But nonetheless, this gives us freedom to have non-blurry images because we use nice scaling algorithm. The downside is that the random filter creates a special type of random noise in the image, obviously, so you can see this here. And the median filter is a little bit slow. I'm saying a little bit slow. Maybe some of you remember from their computer science studies, there is this median of median algorithms. So there is this magic where you can do a median calculation in linear time. We did experiment a little bit with this, but we did not really succeed in implementing a super efficient median implementation for these images. So maybe it's just our experience with programming these algorithms, but our implementation is a little bit slow. So it's comparable to area scaling, which is also slow. But I guess that if you're an expert in medians, you can do this much better. So I prepared one example for the end here to show you that median filter and the attack image, that very nicely the original image is reconstructed. So here you can see this blue sky. In the blue sky, there is this fine grid, these attack points. And in the reconstructed version, really nothing of the attack is visible anymore. Of course, the attack is the image is chosen a little bit to our advantage. Reconstructing a blue sky is, of course, much easier than reconstructing some very structured object. So this is maybe a little bit on our side. So it could be that the median filter creates also small artifacts. However, I haven't seen them. Now, what remains, of course, is the question, is this really the end of the story, or can other people do better? And we try to answer this question ourselves, because I think in adversarial machine learning, it should be standard to always attack own defenses and not just wait for others to do this. There are people that do this all the time. So maybe they want to have a little bit of free time and work on other things. So researchers should always attack their own work. We did this, and it would take some time to talk about this also here, but I just kind of condensed it. So we integrated knowledge of the defenses into the optimization problem of the attack. So this means the attack is now not only looking for misleading the scaling, but it's trying to do this, for example, by computing the median in certain windows and then changing this median. Or in the case of area scaling, try to influence this flat kernel function. Or in the case of random filters, try to make sure that the random selection picks the right pixel. Now, maybe you already know this. When you think about it, it turns out that this is not so easy. Controlling an average, controlling a median, and controlling a random selection is difficult. Simply because you have to change more in the original image than you would normally do. For example, if you want to control the average, you have to add, or you have to make more changes such that this average has a value you want to have. Or if you want to have control over the median, typically you have to change 50% of the pixels because those define where the median is. And if you want to select a random, control a random selection, yeah, you have to at least 50% of the pixels that need to be changed. Otherwise, the random selection will pick something that you have not touched. And what's happening is that once you now run this modified extended attack, it still generates an image and a perturbation. But now, due to these increased changes, we see these kind of ugly pictures that you can see here on the right. What do I mean by ugly? So this is a dog and some grasshopper. And since the attack, the optimization problem has to change so many pixels, what's happening is that these images, the original one, the target one, they get mixed. And if we found in our experiments, not a single case where this mixture was not visible. So this means as a result of our defenses, the attack becomes clearly visible. There might be cases where this is maybe even okay. Yeah. So for example, if I cannot imagine something, but I'm sure if somebody thinks about this, there could be a case where the mixture of two images is still plausible. But in all of the things that we looked at, dogs and cats, it was not very plausible that the dog is half cat and the cat is half dog. So this means that we could not break our own defenses. And maybe this is the reason that I'm explaining this to you. And maybe I'm also not adding too much details, because likely you are interested in destroying our defense. And this is in the nature of computer security. I know this. So new ideas are needed. And if you have ideas, feel free to test them, or you can also ask me. And then we will not necessarily help you, but we kind of support you as good as possible in breaking our defense. That's maybe should already too much commitment. Okay, so let me summarize what you have seen. Maybe I make the summary also a little bit broader so that we can also see a little bit that this is maybe just one example of something bigger. So first of all, the bad news. The bad news is that image scaling is a relatively new threat. And these attacks work surprisingly well. I guess I could impress you with the examples. Yeah, and I would expect that if you build a machine learning system working on images, maybe in the automotive industry for traffic sign recognition, you could be a little bit concerned that somewhere in your huge data set of traffic signs, there is one of these attacks. And as a human, likely you will not notice it. So this means that this can be a problem and it affects training and application. So, okay. The good news is defenses are not as far away as for other problems in machine learning. First of all, we have this area scaling. It's already available. I'm using it now all the time. Even if I'm scaling an image for my website, I would always scale it with area scaling because I know then the image is secure. But even if you cannot, for some reason, use area scaling, you can plug in our median and random filters. You likely can even implement this yourself. It's not so complicated. And you can be relatively sure that these attacks that we described in our work are not applicable anymore. Doesn't hold for new attacks. So this is also something to keep in mind. So we are kind of defending against a particular attack, and we can show that the defense is robust enough. But of course, this is not the ultimate defense. It's just kind of a intermediate result in this long security research history. There's a website. You can go on the website, and then you can get our code implementation and also some examples from the paper. So what remains, and this is kind of the take-home message for you, so like the homework, I would argue here and take the chance to say that I think preprocessing is a very lucrative target for security research. It's boring, this is true, but it's used in a lot of different settings, not only computer vision. And we can even formalize a little bit what's going on in this attack that I showed you. So what we see is that we have a disagreeing view on the same data. The human sees something different than the neural network. And I bet that there exist many other scenarios where exactly the same problem occurs. And I just as some idea. So for example, if we stay with the idea of there's a human looking at something and a machine, we can see already some of these attacks under a different umbrella. But for example, if you know these homoglyph attacks, in which you change a character with a character that looks almost the same, but is slightly different. So as a German, for example, you could use an Ö, that's an umlaut, for an O, and many other European and also worldwide languages have these kind of slightly different looking characters, and you can use those as a replacement. And this is typically done as part of adversarial examples for text. But I would argue it's more a preprocessing attack because it changes what the machine sees in contrast to what the human sees. And therefore, it's not about how the neural network is interacting with this, because the neural network doesn't really see the original text. Another example are these psychoacoustic attacks against audio recognition. Not sure if you have heard of them. So there's a recent research branch on this. So, and they make use of things like MP3 characteristics. You know, as a human, maybe you know that you cannot always hear all frequencies equally well. So if there's a very loud frequency somewhere, nearby frequencies are lost. And if there's a certain frequency peak, also a short moment afterwards, other frequencies are not audible anymore. And there exist attacks on neural networks for audio content recognition. They built on this idea. And again, I would say it's not really an attack against the neural network, but it's more like a preprocessing because we can add information that a human cannot hear, but that the neural network obviously has to process. And then we can create these disagreeing views. And lastly, we can play this game also machine against machine. And then we move maybe a little bit away from machine learning, but we move into security, the classic domain of security. For example, if you have heard of polyglot files, not sure. So polyglot files are files that are characterized as different file types. So one program says this is a GIF, and another one says this is a jar archive. And this is done because there's a disagreeing view on the file. And this depends on ambiguity. And again, it's a preprocessing attack. And what, of course, later happens with the file is different depending on whether it is characterized as a GIF image or a jar archive. Or the same holds for malware. If you have a malware analysis system and you want to analyze, let's say, a PE header, so deep inside the executable format of Windows malware, it really depends on whether you have the same view on this data as the system that later executes the malware. And I would argue this is also related to preprocessing, in this case, parsing. So the point I want to make in a very long-winded discussion is that maybe there are many more needles that we can punch into the preprocessing box. And I don't have it on the slides, but maybe there are even other boxes in these pipelines that also deserve a couple of new needles. And I think this is the thing why I really like security research so much, because we just do not need to kind of work around these needles. We can also punch them ourselves. And this is maybe my closing word. So take this chance to kind of explore new offensive techniques in the realm of everything related to learning-based systems. With that, I'm looking forward to questions.
Thank you, Konrad. So for the very interesting talk, and there's a round of applause, like a virtual or a very sad individual one. So until we meet again in the flesh. So thank you very much. And let me just go over the YouTube channel. So it seems that on YouTube we don't have any questions. So I am going to